In today's lesson, we are going to learn about geometric sequences and series, as well as finite geometric sums. First of all, let's define a geometric sequence. A geometric sequence is when each term is the product of the preceding term and a common ratio. So if we look at this sequence that we see here, we can see that our first term is negative 24, and then as we go from term to term, we can tell the values are getting smaller, which tells us that our R value is going to be less than 1. To find the R value, what we want to do is we want to divide consecutive terms. Similarly, how we found the D value by subtracting consecutive terms, we want to do the same thing here. We can pick any two terms, and I always pick the easiest two to divide. When I divide these two, I get the ratio of 1/4. So basically what this tells me is that each term is 1/4 of the previous term. So A2 is equal to 1/4 of A1, or 1/4 of negative 24, which gives me negative 6. And A3 is 1/4 of A2, and so on. As we can see, that would generate our whole geometric sequence here. Okay, so a couple of tips to help us out. When we're working with geometric sequence, we're going to notice that we are always multiplying or dividing by the same number, which is going to be our common ratio R. If we're working with an arithmetic sequence, we'll notice we're always adding or subtracting by the same number, which we call D. If neither of these rules apply, then we're going to look for patterns to generate our explicit formula A sub n. So common examples of neither is when you have, for example, perfect squares or perfect cubes. Also, another time when we have a neither is when we have a fraction and we write one formula for the numerator and one formula for the denominator. So when we have a fraction and we split the numerator and denominator, and then treat each of those separately as we create our formulas. Okay, so for each of these problems, we want to find the common ratio R and the next three terms in the sequence. So just like we talked about on the previous slide, we are going to take a term and divide it by its previous term. So for example 2, we get the common ratio of negative 2. Now when we go ahead and test this theory, if we take each term and multiply it by negative 2, we get the next term. So my next term is going to be positive 48, then negative 96, then positive 192. If we take a look at example 3 and do one term divided by the previous, again, we can pick any two terms we want, so I would personally go with those two because they're a lot easier to divide than the fractions. 28 divided by 7 gives me 4, so that means I multiply by 4 to get each of my next terms. So my next terms would be 112, 448, and 1792. Okay, pause the video and try the rest on your own. All right, here's the solutions for the next two problems. Okay, when we want to generate a formula for any term in a geometric sequence, we can start by saying that our first term is our first term. And to get our second term, we take our first term and multiply it by R. And to get our third term, we take our second term and multiply it by R. Well, our second term is A1 times R, and then we multiply it by another R. And we can continue in this fashion, and I think you may see where this is going. Whatever my R value is, I am multiplying by n minus 1 R's, or by R times by itself, and my start over. My equation here is going to be A1 times R to the n minus 1 power, because we see that if my n value is 4, then I have to multiply R by itself 3 times. Goodness, I'm having a hard time getting that out. Okay, so this right here is our explicit formula to find A sub n for a geometric sequence. Okay, so that being said, we can use this formula to write the next couple terms, just like how we did with our arithmetic sequences and series. Alrighty, so if we know our R value is root 3 and A11 is 972, we want to figure out what A1 is. So just like we did before, we can list off what we know. We know in this case that n is 11, and a sub 11 equals 972. We know that our r value is root 3, and we are trying to find our a1. That is my unknown here. So if I start with my equation, a sub n equals a1 times r to the n minus 1 power, I can go ahead and plug in everything that I know. I know that my n value is 11, so a sub n is a sub 11. So I can say 792 equals a1 times root 3 raised to the power of 10. Now you might be wondering, how the heck am I going to do root 3 to the power of 10? Well, good news, we have our calculator. And we can also think of this like root 3 is really 3 to the 1/2, and when we raise a 1/2 power to the 10th power, we really multiply those, so it just gives me 3 to the 5th. And if I divide, I find out that a sub 1 equals 4. And since we want to find the first 4 terms, I start with 4, and then I just repeatedly multiply by my r value of root 3. So I get 4 root 3, and then 12, and then 12 root 3. All right, now in number 7, we are given 2 different terms. And just like we did when we were working with arithmetic sequences, we're going to want to create a system. We start by saying that our third term is equal to our first term times r squared, because that's n minus 1. And my sixth term is equal to my first term times r to the 5th. And now that we have our generic equations, we can go ahead and plug in our values for a3 and a6. So we can say that 36 equals a1 times r squared, and negative 121.5 equals a1 times r to the 5th. Now, in this case, we're not going to be able to use polysimult because these are not equations in the form of like ax plus by equals c. In this case, we're going to have to use substitution. So I generally solve for the problem that has a smaller r value, and I'll get that a1 equals 36 divided by r squared, and then take all of this and plug it in right here, giving me negative 121.5 equals 36 over r squared times r to the 5th. The reason why I solve for the equation that has a smaller exponent on r is because now at this point when I simplify, this just gives me r to the 3rd power. So I divide by 36 over on the left, and I get negative 3.375 equals r cubed. And then at this point, I need to take the cube root of both sides. And when I take the cube root, I end up getting negative 1.5 or negative 3/2. All right, so I'm almost done. Now I just have to find my a sub 1. So now, since I know that a1 equals 36 divided by r squared, I can just plug in my r value and square it and divide, and I find out that my first term is going to be 16. All right, geometric means are going to be very similar to our arithmetic means that we learned before. Same idea, it's the missing terms in between non-consecutive terms of a geometric sequence. We're going to set this up the same way. When we see that we have 2 geometric means, that essentially means that we have 2 blanks or 2 unknowns. So we will say 12 blank blank 4 over 9. And just like with our arithmetic means, we were adding the same value. Well, here we are multiplying by the same value, that common value of r. So I can say that 12 times r cubed equals 4 over 9. And just like we saw on our last problems with arithmetic ones, however many blanks I have, my n value will be 1 greater. So now to solve, I just divide by 12 on both sides, and I end up getting r cubed equals 1 over 27. When I cube root both sides, I end up getting r equals 1/3. And then now I can test my theory. 12 times 1/3 equals 4. 4 times 1/3 equals 4/3, and then times 1/3 again equals 4/9, and we are good to go. All right, last topic for us to learn about is our sum formula for geometric series. And this formula is a lot uglier than the one that we used for our arithmetic means, or arithmetic sequence. So first of all, I want to point out that the exponent n that's on r right here is only on the r, not on the parentheses, and that's a common mistake that people make. So just like we saw before, we want to go ahead and write down all our variables. So we have our a1, our r, our n, and our sub of n. And in this problem, I'm asking you to find the sum. So this is my unknown. We can fill in everything that we do know. We know our first term is 14. We can divide to find our r value is -5. And I want to find the sum of the first 7 terms. So n is going to be 7. So then I'll simply say sum of 7 equals 14 times 1 minus -5 to the nth power to the 7th power, all divided by 1 minus -5. Now when you enter this in the calculator, you have to be extremely careful, because if your parentheses are wrong, this will not work out properly for you. Make sure you have parentheses in the denominator. Make sure that you have -5 in parentheses as you enter this all in. All right, we end up getting a very large number, 182,294. All right, pause the video and try the next few examples on your own. Okay, this example 10 can be pretty messy. So we go ahead and we set everything up and we walk through and we solve, and we get to this part, -160 over 1 minus root 3. And unfortunately here we have to rationalize. So we multiply by the conjugate, 1 plus root 3 over 1 plus 3, root 3, and that simplifies to give me a -2 in my denominator, and then that -2 can cancel with the -160 to just give me 80, and when I distribute those, I get my final answer of 80 plus 80 root 3. Okay, we are almost done. All right, last but not least, here we want to work on writing this in sigma notation. Recall that with sigma notation, we use the sigma sign. We write the n equals where we start, which is always going to be 1. Then we want to write where we stop. In this case, since there's a dot, 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 we're stopping at infinity. And then this part in here is going to be my a sub n. Now to get my a sub n, recall that it's a1 times r to the n minus 1 power. Here my a1 is 3. If I do my division test, I can see that my r is 2. So 2 to the n minus 1. So my final answer would be 3 times 2 to the n minus 1. Now I want to mention that in this case, this is not by any means equal to 6 to the n minus 1. You can't multiply the constant with the base. Doesn't work. All right. For this last problem, when we go ahead and we simplify, we can see all the pieces that we need to use our equation. We can find out what our a1 is. We can see we are finding the sum of 10 terms, so n equals 10. Looking at our problem, the number that is being raised to a power is my r value, so I can see that r is equal to 3. And now I just need to work out my formula to find s of 10. All right, go ahead, pause the video, and try this last problem. All right, and our final answer for example 12 is 118,096. One thing I just really want to mention is that when we see an equation in this format, because we know that our nth term formula looks like this, we can recognize the number that is by itself is our a sub 1, and the number that is being raised to a variable exponent is our r value. So just like how we were able to look at our arithmetic formulas and pick out our a sub 1 and our common difference, we can do the same here with our geometric formulas. All right, homework is worksheet 1D, I believe, whichever one is the next one in the series. That is all. Have a good night.